Time for the reaction diffusion. It's a simple idea with two kinds of chemicals. Assuming we have chemical A is being added at a given feed rate. So we keep adding A into the container. And when A has some nearby B chemicals, it will be turning to B. And the B is being killed at a given rate. So this kind of algorithm will produce all kind of interesting pattern given the different feed rate F and the kill rate K. This is the equation, and we can see the we have the Laplacian operator here, because basically we will try to find the gradient, the divergence of the gradient, because we wanted to find when A and B are nearby. So we can see the Laplacian operator here in this formula, and we can implement it in Houdini. So let's see. We see the result is like this. We create this kind of structure by setting a specific kill rate and feed rate. So we are going to use the volume to implement this. First, we use a VDB and create 4 volumes, A and B. Another 2 will be the temporary volume, which will be used later. And we VDB activate it and set the value to 1. And we also prepare a geometry. This will be the chemicals B. The chemical speeds will be inside the sphere. So we simply sample the sphere volume and set it to B. And then we just convert it to the volume from the VDB volume, because we are going to use OpenCL, and Houdini only allows us to use the OpenCL with Houdini standard volume, not VDB. So we are going to jump inside the solver and see the result. So basically in the solver, we just use an OpenCL node to run through the AB temp A temp B volume. And then basically we are just using the formula I just mentioned here, this formula. And one of the thing we have to mention is to calculate the Laplacian, and we simply using OpenCL to sample. It's called the discrete Laplace operator, which we can find in Wikipedia. So we basically use a matrix as a filter to run through the volume. And so we have this 3 for loop, which will run through as an operator filter. So we simply calculate the Laplacian A and B and just use the formula listed in the web page, and then write the result into temp A and temp B. And then we use a write back kernel to write it back to A and B to avoid the racing condition. So when we can simulate for multiple stage, we can see something, the chemical is happening inside. And then we just delete the volume B, because we just wanted to keep the volume A and convert it into use convert to convert it into a polygon. Use an ISO value to get the ISO surface. So we have this kind of structure. So the result will be something like this. And this is trying to create the diffusion reaction by using volume, but actually in Houdini we could also, let's say I have a sphere, polygon, subdivide. I'm going to use a mountain, and actually for each point we can let the chemical reaction happening on the surface of this any particular object. We can just see every point as kind of like containing a chemical and calculate the Laplacian. Basically we look for its nearby points, calculate the Laplacian, and we can do the diffusion reaction on any kind of object surface. But I will talk about it if we have time, rather than using the volume, and it's much more general and interesting.